Hey everybody, this is Larry. This is day 14 of the October Leetcode Daily Challenge. You're 2 weeks in. Congratulations. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. So I'm plugging in the power because I think my power is running low and I forgot. Anyway, today's problem is perfect squares. So given n, return the least number of perfect squares that sum to n. This is a silly problem. Because I think someone told me, and I think I don't know how you can prove this. I would say someone told me that there's a conjecture, or I don't know if someone told me, but I think it's just from the last problem that last time I solved this. I think I read it in the comments or something like that. So someone gave me a thing, so you can do it that way, where there's a trivia or conjecture. I don't know if it's a conjecture or the theorem. I don't know if it was proven, but that basically you can do it with 4 squares with every number. So every number can be the sum of 4 squares. I believe that's the case. If I remember, that would be kind of sad. But that also means that you only have to check for 3, because anything that does not satisfy 3 numbers, you could just return 4. I believe that's the case. And then the other one, you can either, let's see, you can either do some for loops, you can either do dynamic programming. There are a couple of ways you can do it. Let's kind of play around with that then, right? So basically, the way that I would think about it is that, okay, so we return 4 because this is the max number. I actually don't remember this is true, and I don't remember the theorem's name, so you might have to Google it, or I'll leave it in the comments or something like that. But I think that's the case, and that's where when you practice, you'll know these things, even if it's completely useless, if you ask me. But or at least not like, when is that going to come up real life, or when is it going to come up in real life where you cannot look it up, right? That's the other part of the question. But yeah, now we can do for I. We can probably even do something like, I is equal to j is equal to k is equal to 1. So while I times I is less than n, while I plus, and you can actually do something. I was going to, so the more natural way is to write it this way, I think. And this is already taking an operation, so we'll do some math. But you can actually, there is another way to think about squares, which is that, so 1 plus 3 plus 5 plus 7, so plus 2x plus 1 for some x. That's going to give you squares because, this is 1, the prefix sum is 4, this is 9, this is 16, So this is something that actually comes up. I don't know if it comes up a lot, but if you do enough mathy things, this will come up. So you can kind of do it this way as well. So then here you may think, here you start with 1, and then here I2, but here just to. So I'm not going to use the recurrence, but it is something that you can use. The reason why I'm not using it is not for any reason other than my first goal in a lot of problems. I'm going to try to write it to as much. I'm going to write it as attempt to be error-free as possible. Sometimes I will make some optimizations like here, but yeah. It's just me trying to be as error-free as possible because I don't want to make errors, right? So that's basically the answer, really. Oh yeah, okay. So it's the least number. So actually, I got ahead of myself a little bit. Yeah, can it be 1 square? So that is just, let's just say I is equal to I think that's even, there was even a function for this, right? Is that a function, or did I make that up? Is this a Python square root? Sometimes I don't, because there are a lot of languages where that is the case, but I don't remember if Python is one of them. Okay, so that is a thing. So so let's get int if I times I is equal to n, we return 1. So now we do, can it be 2 squares, right? If I2 plus j2 is equal to n, then we return 2. Otherwise, then now we have k2 is equal to n minus I2 minus j2. So then now we check if this is a perfect square. K is equal to n of square root of k2 if k return 3. And that's, I think, pretty much it. Let's run the test cases, and we'll run some examples as well. Of course, I have the wrong answer. Why not? At least okay, let's actually run it real quick. So we have 1, 2, 3, 4, 5, 13, and then just some big number, at least big enough number, too big maybe. Let's run it real quick. I mean, this is wrong for the test cases, so we'll have to see why, but I want to see at least the 1 and 2s are right. Okay, the 1 is correct, 2 is correct. For 2, how did I scroll up? Is there no way to kind of expand this? That part is a little bit awkward because I feel like on the daily exploration stuff you can do this in a more better way. This is kind of a poor experience. Nope, I want the opposite of that. I want this to expand beyond more. Nope, that doesn't do anything. I think on binary search you can do that, but I could be wrong actually. Binarysearch.com. But I'm just a fan. I mentioned it because of that. Okay, so this is like really hard to debug as a result versus the export tab where you can actually scroll down. Nope. I'm just trying to think. Oh, there's a use extent, but oh, okay. I actually didn't know that I can do that, but still, it doesn't solve my problem of it's really hard to kind of look through multiple test cases. Anyway, so let's just do 12 and 13. Somehow, Leetcode still find ways to make things annoying. But anyway, yeah. So it is wrong for 12. Oh, I don't reset I and j, and also we assume j is equal to. So j is equal to I. Yep, I forgot to. I think that's pretty much it. I think I just forgot to reset the loop. I was wrong. Well, I mean, that's part of it, but I also forgot to do this. So hopefully that's right. Nope, still wrong. Huh. Dun dun dun. So we don't check this, but why would this terminate early? So I have 1. This thing is so much harder to use than it was before. Okay, so I guess I'll just remove this. So I'm still learning how to use these interfaces in a good way. But yeah, okay. So I2, it goes to 2. Yeah, so this is 4. This is 2, so it should be 4. Otherwise, K2, okay. Let's print this out a little bit. Maybe I have some really silly typo. 331, that's not quite right, obviously. Huh. Did I mess up something? Because J is 3, but why is it not starting at 2? Do I increment in a weird way? Oh, this is silly. I reused I for this and then I forgot to reset it. That's what I get for being careless. Okay. Okay. Silliness. Been very silly lately, to be honest, which is actually unfortunate. because I've been just eating a lot of penalties. But anyway, let's add a few more. And now I have to figure out a better workflow around this new interface for sure. So yeah, so this looks good. Let's give it a submit. Maybe I get a wrong answer. Maybe that's fine. Oh, look. My other one was very... Ooh. So 18 is 2. Why did I get 2 wrong? So this is 3. Oh, because this early terminates. So, Okay. I mean, I think I was just being careless still. So, yeah. So 1, we know that this is 1. But if this is 3... we may actually be 3. So best is equal to 4. Yeah. Let's say if best is equal to 4 and this is the case, then best is equal to 3. Otherwise, we don't even do the math, right? Well, we don't need to do the math. Wow. I should. I don't know. I just feel a little bit silly that I've been very careless lately. So my apologies, but yeah. 2, well, if it's not 1, it's 2, so I think this return is fine. And then, yeah. I think this sequence of things should be okay. We should add 18. Okay, I do like that they have that, so let's give it submit again. Okay, 562. So yeah, so I probably did it. I think the last time I did it was with dynamic programming or something like that, or maybe even just smart brute force. But know that it is much faster as a result. Yeah, let's see what I do last time. Yeah, I did dynamic programming last time. Cool. Yeah, I mean, like I said, if you don't know this, I guess dynamic programming is alright. And since I did it last year, I think there's a video on it. Let me know what you think about that one. But yeah, this is just basically off that fact. Yeah, let me know what you think. Other than that, Larry needs to be a little bit more careful. But yeah, this is basically linear, I want to say. And the reason why this is... Wait, no, it's not linear. It's exponential, I suppose. And the reason why this is exponential, I think, is that... so I talk about this a bit in a lot of my problems, especially lately. I feel like these problems have been like this where... Anyway, so there are 2 things, right? One is that n is the input, is equal to input. But people, when they say about O of n and stuff like that, is actually, in this case, n in this case is not input. It is actually input size, right? So for example, when you have an array of n elements, the input size is O of n because it has n elements, and it's n elements times some constant thing. But in this case, n is the input number, not input size. The input size of little n, input size is actually equal to O of log n because it takes log n bits to represent this number, right? And of course, this algorithm here is going to be O of square root of n because we just run through the square root of n. So yeah, so this is square root of n or O of n to the 1/2, which if we yeah, so in terms of input size, then this is 1/2. Maybe is it? Let me think about this. So yeah, so this is log. Wait, what am I saying? Yeah, so this algorithm is n of n to the 1/2. Man, my math is really bad today. So this is going to be O of Man, I'm really bad at substitution today. So okay, so input size is I'm mixing n's and log n's here, that's why. So the input is actually log n, right? So let's just set n is equal to log n. Then in this case, we have an n to the 1/2 algorithm, and therefore so what is that in terms of n, right? N is equal to log n, so 2 to the n is equal, let me just do the math, sorry, it's been a while. So 2 to the n is equal to n, so therefore it's 2 to the n over 2. Yeah, that's what, okay, so that's what I thought. So I think the not gonna lie, so the problem is that I actually knew this was recurrence, but I think it's one of those things where if you've done it enough times, you know the identity, so you just kind of do it in your head and you see the pattern enough. But then I forgot how to actually show the work. I don't know how to show the work anymore because I've done this too many times. But yeah, but in any case, so the complexity time is actually equal to O of 2 to the big N over 2, which is of course O of 2 to the N. Roughly speaking, you can debate it however you like, and of course the space is going to be O of n because that's just the representation of because that's the size of your bits for each of your variables will be O of n, so that's why this is so yeah. So this is exponential time and linear space as a result. I don't know that I explained that well, mostly because I confused myself a few times. Anyway, I hope that's good though. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think. I'll hope you enjoy the first 2 weeks. I'll see you soon. Stay good, stay healthy, to good mental health. I'll see you later. Bye bye.